Welcome to another GCBASIC video for the 18F Q24 chip family. These are the set of videos around trying to get things working, and I should do this one, and I'm doing this video retrospectively. So what I'm trying to do is get pulse width modulation working. Simple, one would have thought. Okay, so I was going through the videos, got down to video 14, and it's called using PMW 7 ways to dim the LEDs. And I'll explain the 7 ways in a moment, which one and what's not working, because it's pretty important. Compiler, open source, needs to support the Q24. And so what we've got is this architecture where we take source code, we pre-process it, and I'll just use my pen. We take some source code and we pre-process it, but we suck in some stuff from the DAT file, a DAT file, which is a description of the chip, and I'll show you how we do that in a minute, and some libraries. And from that, we would then get the specific PW pulse width modulation code. It would then go through the assembler, blah, 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 and produce a hex file. Okay? I mean, that's what it does. And so why have I put those two in red? Because that's where we're going to have a problem. I didn't know we were going to have a problem, but that's where the problem lies. And I'll explain that in a minute. So there's an issue in the library, DAT file, and an issue in the library. So what have I got? And let's look at Deskcam. I have got hooked up the standard board. I've got 28 pin Q24, some 4 LEDs, switch pot, blah, blah, blah. Oh, but look, oscilloscope. And this oscilloscope is going to show me the signals, and we can see those signals on the monitor here. Let me have a look. When they're running, we'll get a signal on here. So we can see it, which is really cool. When I did the video, obviously I had more kit hooked up, but essentially it failed. And so I have this Gabtronics little oscilloscope, very useful. I can just shove it on the screen, and it's better than using the very expensive Rygols, because the user interface, that interface is better, to be quite frank. Okay, 7 ways. PWM 7 ways. So look, it's a simple way, port on and off. We knew that was going to work because that's just turning ports on and off. And then there's two others called pulse out and PMW out. Well, essentially, they're just ports on and off, fancy ways of doing ports on and off. There's a 16-bit way, number 6. We just set the registers and it just works. And there's an interrupt way. Well, that was going to work because that is essentially turning ports on and off with an interrupt. The problem is that using CCP, PMW, needs to work. And there's 2 ways of doing it. There's a fixed frequency, and that uses timer 2. And as it says in the comments, very low impact in terms of code. If you want a fixed signal, brilliant. You just type it in, and Hugh wrote that a long time ago, and it just works. But then the same module, that CCP module inside the microcontroller, can be controlled as number 5, variable frequency, variable duty, using timer 2. You could use other timers, right? But all the assembler does the heavy lifting, and it's changing the frequency and duty in the assembler, therefore in the real time. It takes compute power. Number 4, fixed frequency, is from a set of scripts. I mean, the scripts are complicated, but do you know what? They haven't changed in a very long time, because CCP, PMW, is well known, it's established. Okay, it just didn't work. So here's the lab. I was trying to get PMW to work. Let me show you what I was doing. Okay. Now, it's a program, and this one was called 240 CCP PMW Discovery. And I actually don't show this during the demos because it's a little bit complicated, but it helps me understand what's going on. So Control B, Control J to shut all the windows down, and I'll press Control plus to zoom in a bit, okay? And essentially what it does, the program, it selects the chip, sets the PPS. Because we're going to use CCP, And my goal here is to set 4 LEDs to a CCP signal. I just need to set that up. And I've said connect CCP1 to RB0 to 3 LEDs. So that's the LEDs. The rest of this is all constants. Is there a map here of the chip? Oh, that's a bit naughty of me. Anyway, lots of debugging here, and it says, right, hardware discovery before fixed mode, after fixed mode. So let me just, and here's the command, look, PWMOn, and that is all you have to say. You can change the frequency and duty using these two constants. And the scripts in the back end of the library, PWM.H library, do the heavy lifting. So if we run that, and we look at the terminal at the same time, we're going to get quite a bit of info. Happens to be using PIC-AS, doesn't really matter. Is it connected? It's connected. Good. Oh, look at that. Now, let's just disconnect that. And if we look at the oscilloscope, did that send out a signal just then? Oh, there you go. Sending out a signal. Isn't that fantastic? Look, that is really good, right? So it's sending out a signal. It is 38 megahertz. It is up 50%. The form isn't beautiful, but there's two parts to this demonstration. There's a first half which uses, and I'll go back to the terminal. There's a first half in here that is actually for fixed mode, and it turns it on for 10 seconds, then turns it off, and it's these little dots down here, look. And it all seems to work fine because this is all the registers that need to be set, and that's the registers before the command, PWMOn, and then this is the registers after, because it says it, after PWMOn, okay? And it says here the frequency is 38, duty is 50, use these timers is all good. And then here it's all set. And you can see that this one here, CCP1 call, has changed from 00 to some value. And that's the control register for that particular command. Now, I had to fix it. Let me unfix it. I'm just going to comment out what I had to add. Program it again. Program it again. I'll bring in the terminal. There's the terminal. There's the code. I'll clear the terminal and disconnect it when I need to. Okay. Now, it looks like it's working. If I reset it, power cycle it. I'm going to power cycle it, reconnect the terminal, and we'll look at what happens. It's got some power, and it's now turned on. Have I saved it? Oh, yeah, Wally. That's my fix. That's as it was before. Right. I've now reverted the PMW as it was, okay? So it's going to program it, and then we're going to look at the serial terminal, okay? Connect, clear. Now, it's important that I reset the beautiful, it's done it. Reset it. Disconnect the terminal. Let's just look at this. CCP1 was 0 beforehand, and this is it afterwards. CCP1 is set to 28. That's 28 decimal 1C. But it's not working. There was no signal to start with. So there's two halves to this. Remember, there's a fixed half and a fixed half and a variable, and the fixed half was failing, and it's failing because look here, these registers, see the cache register is 28, T2 TPR is 105. All these registers are the same values, and so if they match up, these values match up with the top set, so that matches here, then I'm right into the right register. The script is right into the right register, but this one here, CCP1 con, I spotted almost immediately was incorrect. I thought, what's what's going on? That should be set to some value, but it's not set at all. It should be set, and I couldn't figure it out because the cache is wrong as well. And so I looked at it and thought, well, the cache is equal to that, but it's not sending a signal out. And what it is, the root cause of this problem is Microchip. I'll go into some depth. Up on GitHub, you can download this software. This software generates the DAT file. And it's actually, I've got it inside a folder, and I can walk you through it. And I'm going to go into a folder that's called XC8 to ink converters, because we need to take some source from Microchip to make all this magic work, okay? And down here, in the depths of this thing, there's a set of executables that do all the conversion. So let me just open up that, and I'm going to open up a command prompt, open it here. And if I go dir start.exe, the latest version is 6.2, so it's this executable here. Look, I ought to archive the rest. I will archive the rest in a minute. And if I just run that, it will list all the chips that are available for conversion. There you go, loads of them. Absolutely loads of them, okay? And if I pass it a parameter, pick 18F, 26, Q24, it will then convert the source files that are inside of mplab.x 6.2 and convert them into an ink file that you could actually use in mplab. But it's what we need inside of GCBASIC because we convert that into a DAT file. So if I just put that out to a file, I'm going to call it t. There you go. I always use t, by the way, because if I see t.text, I just delete it. I'm going to take a copy of this, and I'm just going to open that file inside of GCCode. 8/t.text. And that was converted just a few minutes ago, and it will say all that stuff in here. And it says these are the source files it used. Now I'm going to get rid of the camera. These are the source files it used. Now if I search in here for CCP1 call, it shows me the register. Now no code in GCBASIC has written this, okay? This is a conversion of the source files that we used that were listed at the top. Recap. So, we haven't done any manipulation at this point. CCP.com. It's in some sort of hexadecimal address. Doesn't really matter. And it says later on in this file that there are some bits associated with this. And they go on. It's all these bits. And if you look in here, interestingly, this is bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6. There's one called enable. And that's in bit 7. And that's not been set. It's not been set. Why has it not been set? Because if I search in this file for EN, a load of spaces, EQ, and a hexadecimal number, I find 15 of them. And because Microchip have just given up on the naming convention they implemented back in the day, they've given up. They've particularly given up on the Q24. They've given up on the fact that every bit used to have a unique name. Every bit had a unique name. Now, every bit is unique in the sense of this particular one is called cm1con0.en, and the next one is called cm2con0.en, and that would point to .7. And most of the enable ones, look, are 7. But one of them, oh, there's 24 of them. Look. Oh, this one, this bit is 0. Now, Why is that important? It's because GCBASIC and EEPROM and PIC-AS, the things that we compile into, need a flat world. It's a flat world. You can't have two things with the same name. EN is not unique. You can only have one EN, and you can only, that's it, flat fact. You can only have one register with one name, and you can only have one bit called EN. Everything else has to be adapted. It just has to be, because otherwise there's no way of finding it. There's no way of addressing it. I call it a flat world. It's a flat naming space, and everything has to be unique. And whilst this one here is ICSPEN.EN, that doesn't make a flat world. Every bit in its own has to be unique. And that's the way it was, that's the way it used to be. But very recently, because Microchip have moved away into these XML files and they don't really care about the legacy of PIC-AS and MP-ASM, they've given up on all that. And they just call everything EN and they don't worry about it. Because look, they clearly were worried about div 0 had to be unique, so they've stuck CLKR div 0. So they've created duplicates themselves. They know there's a problem in that space, so therefore they just give it uniqueness. So this bit 0 in this particular address has three different names. It's called div 0 and another one called div 0, but there's another one called CLKR div 0. It makes it unique. And I trust you, if I go into here, I'll only find one of those in this file, because they have hit a problem and they therefore have renamed this. Let's go back to the problem we're looking at, which is CCP1 con. They have clearly hit a problem with out. Now, out is probably many times in here, and to be quite frank, that's on bit 5. Look, we'll have a look. Oh, bit 5. There must be another one. They must have hit a problem at some point where they've renamed that, but they didn't do the same for EN. So they haven't created. So what they did, we see it, look down here, like it says CCP1 enable. So they now sort of go, oh, we better stick another one in. Now, if I go back 2 releases into like a Q84, this is not a problem, because there weren't that many registers. There were no other registers using EN, or all the ENs were equal to 7. Therefore, it's a flat world. This bit was equal to 7 on every instance. But there's one instance in here where it's 0, and that confuses the compiler. Because if we look inside what happens next in our generation process, it takes this file and then converts that into a DAT file. Let's have a look at a DAT file. And this DAT file has been through the processing. I open up PIC-info. So what I've got is a problem with this bit. It's not been set. If I look at the bits in here, I'm looking in PIC-info now. I'll zoom in. I'll come into here, and I can already see an EN here. Look, EN underscore. I can already see one of them. Like CCP1. Is it CCP1 con 1? CCP con. I'm just going to put that into the search in here and hit enter. Oh, why has that not worked? It says it can't find any of them. I don't quite think that's true, actually. Is there a register called that? CCP1 con. Wait. What? For some reason, it's not finding it. Let me do a search another way. SPI. I'm going to reselect it in here. Bits. Let's just reloaded it. Look, there's obviously something I missed. CCP1. There we go. CCP1 con 0. Now, the inc file that we were looking at previously in that editor is now pre-processed. It's pre-processed and reprocessed into the DAT file. And in here, it makes other changes. Okay, so here we have CCP1 con. It says in here, the enable has been called CCP1 con enable, which matches up. If you look beneath, oh, it doesn't match up. Oh, no, of course. What the conversion process does, it knows that EN is not flat. And so our process inside of the DAT generation says, oh, I need to stick a prefix on here to make it unique in the planet. And the planet being the planet of this particular chip. So CCP1 con enable. So that bit now bit exists inside of GCBASIC, so we can use it. What else is on 7? CCP1 enable. That's exactly as it was inside of the source file, and we got a number of them being created. But what this means is that EN that existed up to the Q24, EN was unique, and it was unique always on bit 7. The DAT file has said, hold on a minute, there's a problem here. This is no longer unique. It's got two enable bits, one on bit 0 and one on bit 7. I have to make them all unique. Okay. And so what happened is, over in the script, the library, it said the following: set the .en to 1. And the first instance of .en it found happened to be 0. So it set bit 1. It set bit 0. And so it just didn't work. Now, I could change the whole thing and go, oh, well, because of the Q, because it's a Q24, I can set this bit here. I now know that it's the bit's been renamed. It's called CCP1 con underscore enable. I'll just change the library forever, and it would actually break just about everything. It would break all that went before. So what you can do quite cleverly in GCBASIC, you can do the following. You can say, if this bit exists, and it will only exist on the Q24 at the moment, but it will resolve it for all cases in the future, then set that bit CCP1 con underscore enable to 1, else leave it as it was. This took me quite a long time to figure out, and I've seen other instances in this chip where things have been renamed. I'll show you another place it's been renamed. Let's look at the register. PR2 has got another register that's appeared called T2PR. PR2 is the period register for timer 2, and it has always been called PR2. And if you look at the address, it's hexadecimal. I'll do it in decimal. 798. So it's the same register. It's just got two different names now. It's got T2PR and PR2. Well, guess what? Inside of PIC-AS, they've dropped PR2 for this particular chip. It's gone. It's disappeared into the, I don't know where, but it doesn't support it. So you now have to use T2PR. And so the scripts in the libraries have to take care of all this, otherwise it will fail. But back to our problem here, which was getting this one going. I added in this if-def and set it using this naming convention, or leave it as it was. Now this can skip was something Hugh implemented, and basically if that bit exists, then it will set it. Okay, can skip means don't issue an error. Okay, so if I save that, press function key F5, go to Zen mode, bring up the terminal, connect to the terminal, clear the terminal. We'll look at the results. Programming it, we have a signal. I'll just disconnect it. It's going to flash off as it moves on to the variable, because I knew the variable one was working. There we go, it's working. If we look at the results inside of this, inside of our little debug window, it says CCP1 con and the cache is now has its top bit set. Look. Ooh, ooh, that's why it's working. CCP1 is 9C, and now it's 9C down here. That's pretty cool. So things are starting to work. However, then I noticed only when in this bit of debug program that I had to change. In this debug program, I had to change something else. Now, what was it? I had to change this. If T2PR, if that exists, then use that in this bit of string. Okay, pull that register out. I'm trying to remember what the issue was. If I just comment that out, I think it's when it compiled it. There was an error inside of MPLab. Yep, there's an error inside MPLab. Look. Undefined symbol, PR2. If you can't quite see that, I'll just pull it up. Undefined symbol, PR2. What? How does that work? Well, let's go back into t.text. PR2. PR2. But it exists here. And I couldn't figure that out. And the only way I could find out, the only way I could find around that is to not use it and use the one that's called T2PR. And I haven't figured out what the issue is. There's something else going on inside of PKS that says you cannot use, I'm so sorry, you cannot use PR2. And I don't know why. Control J, and so see if I can figure it out whilst I'm on here now. So it's in the .s file at line 2594. Function key F4 open S. Control G 24. What was it? 2595. Was that it? Oh, open. 2495. Let me just recompile it because I forgot the number. So this is an error code coming back from PKS or MPLab. So Control G 25. There we go. 2594. 2594. And it says here, move the register PR2 into byte num. That's quite clearly where the issue lies. It also says it down here. But I've only got one error. Or have I? Let me look at the error file. Here's the error file. Aha, there's more. Oh, no. No, that's fine. The error, undefined symbol PR2. Now, I don't know why it's done that, but I have a funny feeling I've got to... Oh, what's I done here? Here we go. The issue is in the assembly. I'm going to look in the list file. Searching for PR2. Could have done a bit better than that, to be honest. 213 of them. That's interesting, actually. This will tell me where the problem. Oh, look. That's TP. That's T2PR. Well, considering that we're using the microchip source file for the names, it quite clearly that PR2 doesn't exist. This is their register. This is microchip's list file, not mine. It fails over here. Look, it says here it fails because it can't work. I don't know. I have no idea why it's failed. I don't know. It says that I don't know what that is. It says I don't know what that is. PR2 is an undefined variable. We should be able to see that actually inside of the .s file. Watch this at the top. I should have looked up here the other day. Nope, it's not been created as a variable. So quite clearly, there is a difference here between what we're consuming from the GCB conversion process to matching that up with what PKS is using. There's a difference somewhere, and PR2 just is not in their setup files. It doesn't exist as a constant or a register address or a variable. So therefore it throws it away because this 00 says it's an unknown. So 2PR should be a 0 1 E. If we look in here, 3, and we can see it says the same address. So there's a mismatch somewhere between what PKS is compiling and its registers and what we've got. And I just don't know. Maybe they do magic. They do delete registers. So I've noticed that registers are in the XML just disappear. So the way to fix it is always to refer to to T2PR if it exists. And so what I did in my code, I said, if that exists, then show something else. Use the old one because you don't know if it's going to exist. You just don't know what it will be in the future. And that's how that sort of displays it on the terminal. But essentially, Microchip are changing the game again. They're changing register names. They're not maintaining a flat space anymore. It's going to get harder as time goes on to maintain a high quality product because we're going to have to keep checking all these register names and see what works and what doesn't work. And this is a really good reason why I use PKS because it just makes sure everything still works properly. Okay, so what did I do? Let me go into my PowerPoint. So let me go back to my PowerPoint. So PMW registers and register bits are fundamentally different. There is a difference in them. There may be others, but I didn't detect any others. But I changed pulse width module PWM.H. I just put that little if defined to sort of make it work for us. And now it'll work for anything that uses that format in the future. Because remember, I don't want to be changing the DAT file by hand because it will never, ever, ever work inside of PKS. If you manually change the DAT file, whilst it will work for you personally, it will never work consistently. And I want to generate the DAT files fully automatically from their source files. I don't do it like I showed you here. There's just a batch file that does all the conversions for me. So PWM updated. Something's different about the naming convention they're using for for registers anyway. I can understand why they're doing it because they have given up on the flat world. Getting the basics operating, enjoy.